All right, next up, we have Emily Kraschel. Whoosh, yeah.
Hey everyone, I'm Emily and I'm a sports science technician at the University of Oregon. I'll be speaking on how we've been using our workflows within Azure Machine Learning for our athletic data analysis. So I'm a sports science technician. What exactly does that mean? Basically, I handle data for everything high performance athletics at UL. Our general goal with collecting, analyzing, using data is to try to keep all of our athletes healthy, available, and performing well. That's our bottom line as a department. And we do these by collecting and measuring load and volume data, lots of performance metrics and tests taken at different intervals, some daily, some weekly, some once in their entire time at Oregon, and by looking at all the injury data from our wonderful medical staff at UL. We have online platforms for sports science data that host and automate reports for us anytime we input new data. And then that data is available to export manually to Excel or through an API to R, which is what we generally prefer to use. And the data is used by sports scientists in the performance department, strength and conditioning coaches, sport coaches, the athletic trainers. Many, many people in athletics use the data that we are collecting and sifting through. What all of the athletic staff does is what we like to call working fast, all of our day-to-day operations. We're collecting lots and lots of data. Every day for football alone, for example, we have 70 GPS units on the field collecting 100 hertz data for an entire multiple hour practice. And so that data goes and needs to be stored. We conduct basic analyses on this data. And then the performance staff and the sports coaches use it to make daily decisions. And these aren't decisions months down the line that we have time to clean for and do in-depth analyses. These are who's going to play in the game tomorrow night, right? So this is a very fast turnover type of work. And these images are just some of the tests we conduct on a regular basis. That kind of conflicts with the slow work that we generally think of when we think of data science and long-term research. The things like data cleaning and high-level validation, the in-depth reports and aggregation that give us those nice, rich, new conclusions, advanced analyses, and frankly, just the chance to step back, connect the dots, and evaluate what exactly we're doing here. So it's working fast over at athletics and the working slow that it takes to do data science and produce papers have really conflicting needs. The nature of athletics data means that things are constantly being added to, constantly changing. We're always going, oh, there's this other thing we should be testing for. Let's add that. Also, we can't exactly have a controlled experiment. Wouldn't do very well for our football team or any of our other teams if half of our players were a control experiment eating popcorn on the couch and half of them were at practice, right? So we can't exactly conduct science in that way. And in our workflow, there's a lot of bottlenecks and stopping points. In our old framework, with all those bottlenecks, it worked really well for that fast work. We had automated reports via a dashboard through a web-based software we use called Smartabase that hosts most of our data and then just pops out some basic statistics that we can then give to coaches so they know exactly what their players are doing. But it was very, very difficult for the slow side of our work. It was challenging to figure out what our new metrics were that we wanted to put onto that dashboard for the coaches. We had no central source for raw instrument data. We're collecting things from 7 or 8 instruments generally on a monthly basis for every athlete. So we needed a centralized place for that raw data. All of those instruments have unique IDs that didn't always talk to each other well in this web-based application. And lots of different versions, different places, constantly generating new files, which meant my RStudio had so many CSVs, as I'm sure you can imagine. So we needed a new framework. my little laptop storage needed new framework. We wanted to improve the outcomes. We wanted more complete data. Generally, we want our analyses to be as robust as they can, even though the turnover has to be really fast. We wanted to aggregate all this data into one place so that our team didn't have to keep jumping back and forth between different applications and different APIs. We needed more computer power. Again, we're collecting lots and lots of data. 100 hertz for 2 hours. It's a lot of data points. And we needed less duplication and more complete data and the ability to share things with one another within our team more easily. We work across athletics, which is at Autzen Stadium on one side of the Willamette River, and the Department of Data Science on the other side of the Willamette River. So it's not always easy to share things back and forth. Enter Azure. We chose to use Azure machine learning to help solve a lot of these problems, and we've been pretty pleased with how that's gone. But what exactly is Azure? It gives us an analysis that we can do in a Jupyter notebook or a built-in studio. And you can do that in R, Python, Julia, and a couple other languages. This is useful because our team works in multiple languages. So I'm primarily in R, as I'm sure most of you are. But we also have team members who work almost entirely in Python. So it's nice that Azure talks to both and can put both of those languages in the same machine learning framework. It has a terminal that you can use, nice configurable compute. So each team member or each task can have a compute that can do exactly what they need it to. It can run job pipelines, so we can put in little building blocks of code to go and complete different things without having to duplicate, come up with new names, worry about copying and pasting things wrong. Importantly, it also loads and stores our data. So now when we run through and make a new data set, a new file with our millions and millions of data points, it can load that and store that, and anyone on our team can call that up. And because we're working with that HIPAA-protected injury data for all of our athletes, it's secured behind a UO login. So nice and secure for our purposes, makes our IRB really happy. So we have this new framework now with Azure. We still use that automated dashboard for the day-to-day, telling coaches what's happening so they can adjust things for the next morning. But Azure is much better for the slow work and has allowed us to really take some meaningful steps in our more long-term concrete research. We're able to step back from the constant stream of data, really manage version control with the data we're seeing. We're able to pull from all the different instrument APIs into one place, one code. Easier merging from the variety of IDs because we can have just one building block that sorts out all the IDs for the athletes and organizes everything really well. The data all lives in one place, and very happily for me, it's easy to maintain the most recent versions, and everything is stored in the cloud. So I no longer have a million athletics CSVs sitting on my computer. So now that we have this wonderful framework, what are we looking at? I'm hoping to give you guys a little glimpse into what we do in the performance team at U of O so that you know what we've been using Azure for. We're looking at hamstring injury predictability, trying to predict when somebody's going to get injured so we can maybe dial it back a little bit and prevent them from popping a muscle. We're using discrete time survival models to do that and other injury-related projects. And we really want to dive into the difference between genders. There's a big gender deficit in the sports science field where effects on men are studied much more than effects on women for a large number of things. So we're trying to judge the difference between the genders in relationships between metrics and response to training. One specific example of that last one is a recent project that we've been working on something called a counter movement jump analysis. So this is a counter movement jump, has a couple phases. Have the eccentric phase when you're squatting down, the amortization phase when you kind of arrest yourself at the bottom of the jump, and then the concentric phase when you shoot up and jump as high as you can. Within this jump, for this specific analysis, we have a couple variables that we were interested in. We're interested in that eccentric rate of force development. So how much force are you generating while you're squatting down, getting ready for that jump? And we're interested in jump height, which is how high you're jumping. So our research questions were, is there a difference in relationship between these two variables, between men and women? And can we change either of these variables through training while an athlete is at Oregon? That's ultimately what we want to do. We want to make our athletes better. So first we looked at the gender differences. That top line is the men and the bottom line is the women. We can see that the relationship between eccentric, deceleration, rate of force development, that force you're generating while you're squatting down, and jump height is has a stronger correlation for men than it does for women, and it's a little steeper. So the more force you generate, the higher you jump is true for men far more than it is for women. We then put all this into a nice little regression model. And we can see the kind of a nice visualization of this model here. So we regress jump height on that rate of force development, the sport, which we separated by gender for this analysis, and an interaction term between the gender and the rate of force development. So you can see in this top oval here that men's sports generally have a steeper slope, a higher intercept, whereas the women's sports tend to have a much flatter slope, lower intercept. We're interested in sports that break this pattern. For example, that orange arrow is pointing at female track and field athletes. Their slope is quite flat, much like the other women's sports, but their intercept is far higher, which means that they're in general jumping a lot higher. We were really interested in that and just the difference in slopes between genders. We were also curious to see if we could train this, if we could train other women's sports to jump higher, and if we could train people to really harness that eccentric deceleration phase of development. So then we looked at training response and showed that individual change when regressed over their entire time at Oregon had some interesting patterns. Generally, that rate of force development improved a little bit, but not much. Jump height improved quite a bit, and the ratio between the two, so just so we can see the relationship, barely changed at all. And so this tells us a couple things. It tells us that training at U of O is improving athlete efficiency, but not specifically the harnessing of this one part of the jump. So it means we're training really strong on other aspects of the jump, but not this eccentric phase of the jump. And while that may seem kind of like it falls flat, that's really interesting when we look at our strength coaches and the methods that they're implementing and other things that we can bolster to help our athletes jump higher. So that's a little look into the kind of things that we're looking at using Azure ML. I'd really like to thank the rest of our little team at U of O Athletics, the U of O Department of Data Science, and the Athletics Department, and the WUSI Human Performance Alliance for making this project possible. Thank you.